This is our last practice problem. This is 16.9, number 7, the last of the divergence theorem questions. And true to form, we are not going to try and perform the flux integral. Instead, we're going to express this as a triple integral over our volume of the divergence of the vector function dv. Okay. Well, in this case, we're going to definitely use cylindrical coordinates because the geometry of the problem just kind of demands that we do. So first we need to find the divergence here. So divergence of f is going to be equal to partial with respect to x is y squared, partial with respect to y is z, and partial with respect to z is x squared. And you can see how nicely that works out. This is basically r squared plus z once we make the polar conversion. So that's going to be our argument. And with polar, the only Jacobian we add is an extra r. So wow, that's a really easy integrand. And then our limits are going to be pretty easy. Pi goes from 0 to 2 pi, or theta goes from 0 to 2 pi, and our radius goes from 0 to 1, and z goes from 0 to 4. So there it is, 0 to 4, theta 0 to 2 pi, and our radius from 0 to 1, and it's r squared plus z, and then the Jacobian r d theta dz. So there it is, pretty easy to build. And once we integrate the whole thing, we get 10 pi. So there it is. The real lesson in the divergence theorem is to not do the flux side of it. Instead, it's just a lot easier to integrate the divergence over the volume, especially with how much experience we have integrating over volumes in multiple geometries. Is there value in the flux side? Yeah, sure there is, but I don't think so for the divergence theorem. There's value in the flux side because sometimes it's easier than doing a line integral is you can go ahead and do the flux. So sometimes integrating over a surface, that's just easy to integrate through the boundary. So there is still value in finding that flux integral, but not in the divergent theorem.